Every single second, millions of data packets are racing across the globe, tiny pieces of your photos, your messages, your videos. But have you ever stopped to wonder how in the world they all arrive in one piece, totally intact? Okay, let's dive into this because behind the scenes, there's this whole system of invisible guardians at work.
You can think of the internet as this massive chaotic highway. Each little piece of your data is like a tiny car going at unbelievable speeds. And along the way, it faces all kinds of hazards that can corrupt it, changing it from what it was meant to be. Without some way to manage these constant threats, our digital world would just be a mess of broken files and jumbled up information.
So, who are the culprits causing all this chaos? Let's unmask the four most common digital villains that networks are up against every single day.
First up, you've got things like electrical spikes and power surges. A sudden jolt of electricity, maybe from some faulty wiring, can literally flip a binary bit from a 0 to a 1, which completely changes the data. Then there's interference, and you might be surprised, even your microwave oven can disrupt signals. Of course, we also have malicious actors like hackers who can intentionally cause errors, and finally, there's just plain old hardware failure. A network switch just gives up, and poof, your data gets scrambled.
Okay, so with all these villains running around, networks obviously need a hero. And that hero comes in the form of a surprisingly simple yet incredibly clever system, a kind of digital detective designed to spot errors the very moment they happen. And this detective is called parity checking. Its one and only job is to look at the data that arrives and give a simple thumbs up or thumbs down. It doesn't need a ton of computing power, but it is an absolutely essential first line of defense. So how does this detective crack the case? Well, it all comes down to a really simple agreement that's made before any data is even sent. Think of it like a secret handshake, based on one simple rule. And that secret handshake is brilliantly simple. Before they even start talking, the two computers just agree on a single ground rule. It might be something like, hey, for this conversation, every single piece of data must have an even number of ones. That's it. That one simple agreement is the entire foundation for catching errors. So let's break down the process. First, the sender and receiver agree on the rule. We'll just say even parity for this. Then the sender counts up the number of ones in the data it wants to send. Now here's the clever part. It adds one extra bit at the end, called a parity bit. If the count of ones is already even, it just adds a 0. But if the count is odd, it adds a 1 to make the total count even. Finally, the receiver gets the data, counts all the ones, including that parity bit, and if the total isn't even, it knows right away an error occurred.
Okay, theory is one thing, but this is so much easier to understand when you see it. Let's walk through two examples where the agreed-upon rule is even parity.
All right, in this first case, computer 1 sends a byte of data. Computer 2 receives it and does a quick count. There's a 1, another 1, a third, and a fourth. 4 ones in total. Since 4 is an even number, it matches the rule. The data gets a check mark. It's considered correct, and it's accepted. But now look at this. Let's say a power surge zaps the line and flips one of the zeros into a 1. Now when computer 2 gets the byte, it counts 7 ones. Well, 7 is an odd number. This breaks the even rule and boom, alarm bells go off. The computer immediately knows this data is corrupt. And this just perfectly shows how effective a simple counting rule can be. So our detective is great at spotting trouble. But, and this is a big but, it's really important to understand its limitations because there's a huge difference between knowing there's a problem and knowing how to fix it.
Yeah, this quote from our source really nails the crucial point. The check tells the receiver that the data is bad, but it has no idea which of the bits is wrong. Was it the first bit, the fifth? It just can't tell. And because it can't pinpoint the error, it can't fix it. The only option is to discard the bad data and ask the sender to send it all over again.
This slide really sums it up perfectly. On the left, parity checking is an excellent flag raiser. It can tell you an error exists somewhere in that chunk of data. But on the right, you can see its limits. It can't tell you where the error is, and it definitely can't fix it on its own. It's a detective, not a doctor. And that's really the key takeaway here. Our incredibly complex digital lives, all our streaming, browsing, and communicating, are built on layers of these foundational systems. Simple, clever rules that, when you stack them together, create the reliable and orderly experience we all depend on. It really makes you think, doesn't it? If a simple odd or even check is just the first, most basic line of defense, what other, more sophisticated, invisible guardians are out there, constantly checking, correcting, and protecting your data as it flies across the globe?